In our next example, we're again going to be finding the volume of a solid formed by rotating a region, but instead of using the disk method, we're now going to be using the washer method. So first, I would like for us to set up the region in example 4 and look and see, well, what's different between this example and the other regions that we've set up so far. So let's begin by sketching the region. I'm going to go ahead and set up my X and Y axes. And then I have some curves that we need to sketch. We need to sketch y is equal to 2x squared. That's a parabola that opens upward, has a vertex of 0, 0. We also need to sketch y is equal to 0. That is simply the x-axis. And then we also need to sketch the vertical line of x is equal to 2. It's a vertical line that's about right there. So there are our graphs, and this here is the region that we will be rotating. We're rotating about the y-axis. So as we rotate about the y-axis, we'll see kind of like a bowl-shaped region formed like this. Notice that the region that we form when we rotate is hollow. It has a hole in it. So what I mean by hollow is that as we rotate this region around the y-axis, we actually kind of do, I'm going to try to make this seem like a 3D figure as best as I can. We kind of do form like a bowl shape, right? So this region that I have here shaded in gray and the region that I have here shaded in black forms is actual solid of it. Everything in between here, there's no solid in this region here that I'm forming in yellow. So technically, when I spin that black region around the y-axis, we actually do make like a literal bowl shape where I could pour, say, milk into that bowl, into the region that's shaded in yellow. How is that different than what we've done before? Well, if we look back at example 3, the region that we rotated around in example 3, when we took that region and we rotated it about the line x is equal to 6, this shape here that we form is not hollow. It's all solid, right? So this also kind of makes a bowl shape, but it's a bowl that's completely solid through. If you were to pour milk on top of it, you would be pouring milk onto a flat surface, not a hollow surface, and the milk would make a mess. How do we see that when we start to draw our representative rectangle? So I'm going to erase what I've kind of sketched in here to help us see this, but not the graph, because we do need the graph. Well, we have two representative rectangles because we have a representative rectangle that I will call capital R that goes from the axis of revolution all the way to the end of the region that we are rotating. That right there I will call capital R. And we can see that that capital R has a length of 2 because I know that that green line is the line x is equal to 2. But then there's another region, another R value that I will call little r that's not in the region at all. That little r only covers the region that is hollow when we form that solid. So that little r, let's talk about what the distance of that is. We could think right minus left. The right side of that purple line is touching the red parabola, which is y is equal to 2x squared. Now, if we pay attention, our representative rectangles run horizontally. They hit the y-axis. That means when I go to set up my volume integral, I need volume equal to pi, the integral from a to b. Everything on the inside of here now needs to be written in terms of y. So I'm writing this as capital R of y, little r of y squared dy, to really emphasize that when we find our capital R and our little r, they need to be written in terms of y. Again, notice I don't just have one capital R squared. I'm now using the washer method where I have a capital R and a little r. And it's all because of this space in here that is not included in the solid, or that hollow space that we get in that region when we rotate it. So back to us finding little r. We said that the right side of that purple line hits the red parabola, but we also said we need this equation to be solved for x so that we can write little r in terms of y. So when I solve for x by dividing both sides by 2 and then square rooting both sides, I would take the positive square root since we're on the right half of the y-axis, and I would get that x is equal to the square root of y divided by 2. So capital R is the square root of y divided by 2. So now that we have our capital R and our little r, we can go and continue with setting up our integral. So we have pi integral. We do need our limits of integration from a to b. Remember that everything in this integral is in terms of y. So the limits of integration are this lower y value from this region here. Lower y value is 0. Upper y value right there at this point happens when the vertical line of x is equal to 2 is intersecting the parabola of y is equal to 2x squared. So I can figure out what this y value is by just plugging 2 into the parabola. And 2 times 2 squared is 8. So that's the point 0.28. Our upper limit of integration is 8. Now let's take our capital R and square it. So we have 2 squared minus, let's take our little r, which is y divided by 2, and square that. And all of this is integrated with respect to y. So simplifying our integrand, we have 4 minus y over 2 dy. The integral of 4 is simply 4y, and the integral of y divided by 2 is y squared divided by 4. Increase the exponent by 1 and divide by the new exponent. This is evaluated from 0 to 8. So we have pi multiplied by 4 times 8 minus 8 squared over 4. And from that, we are subtracting just 0. And we plug our lower limit of integration into both of those terms, they go to 0. So we are left with pi times 32 minus 16. 64 divided by 4 is 16, to give us our final answer of 16 pi. In example 5, as always, we begin by sketching our region that we will be revolving. We have a parabola of x squared plus 1. That's a parabola that has been shifted up 1. So I know that this is the point 0, 1. We have the line y is equal to 0, which is simply the x-axis. And then we have the vertical line of x is equal to 1. I'll put that about right there. So the region that we are working with is this region right here. And we are going to be rotating this region about the y-axis. So we'll be spinning about the y-axis. So we form a 3D shape that looks kind of like this. Notice that the 3D shape that we form does have a hollow part right here, right? All of that right there is hollow, is not filled. That is our indication that we need to be using the washer method with a capital R and a lowercase r. Our rectangles run perpendicular to our axis of revolution. So our capital R spans the entire region that we are rotating, and our lowercase r, it spans the region that is hollow. So we have the length of the orange segment is our capital R, and the length of the purple segment is our lowercase r. So let's find those. I'll start with capital R. That's pretty straightforward. It is simply 1 because that green line is the vertical line x is equal to 1. So the length of that orange line segment is just 1. Now let's find the length of the purple line segment. The length of the purple line segment goes from the y-axis to the parabola. Now the parabola is y is equal to x squared plus 1. When we look at those rectangles run horizontally and they hit the y-axis. That means that everything in our integral needs to be written in terms of y. So I need to solve this equation for x. So I'm going to subtract 1. I get y minus 1 is equal to x squared. I'll square root both sides, and I'm taking the positive square root since we're on the positive half in quadrant 1 to get that x is equal to the square root of y minus 1. So this distance here in purple, the right side of that is on the graph of the parabola. We found a better way to write that. It is the square root of y minus 1. The left side of that is on the y-axis. That's 0. There's nothing to subtract from that. So our little r is simply the square root of y minus 1. Before I go set up my integral, let's find our limits of integration. Everything is in terms of y, so we need to make sure our limits of integration are also in terms of y. The bottom limit is simply 0. This region starts down here where y is equal to 0, and the region goes as high as this point. So we need to know what is the y coordinate at that point. Well, I know the x coordinate is 1, and to see the y coordinate, I can simply plug 1 into the parabola. The parabola is 1 squared plus 1. This y equal to x squared plus 1. So when I plug in 1, I get out 2. So I know my limits of integration are from y equals 0 to y equal 2. So our volume is pi multiplied by the integral from a to b, capital R squared minus little r squared, integrating with respect to y. We always integrate with respect to y when we are working with the Disker-Washer method and a vertical axis of revolution. So we have pi multiplied by the integral from 0 to 2 of capital R squared is 1 squared minus little r squared, the square root of y minus 1 squared, dy. I'm going to do some algebra to simplify our integrand. We are integrating 1 minus y minus 1. Be careful with your signs there. I will distribute that negative. So on the inside of the integral, I simply have 1 minus y plus 1, which is 2 minus y. Integrating with respect to y and not dropping the pi, we have 2y minus y squared over 2 that we are evaluating from 0 to 2. I will first plug in my upper limit of 2. 2 times 2 minus 2 squared over 2. When we plug in our lower limit of 0, we just get 0 both times. So we're left with pi multiplied by 4 minus 2 to give us our final answer of 2 pi. I'll begin this example by sketching the region that we're working with. Make sure and label both your axes. I'll sketch the line y is equal to x. It's a line with slope of 1 that goes through the origin. Then I will sketch the horizontal line, y is equal to 3. And I will label it because we will have another horizontal line that we're sketching. We have a vertical line at x is equal to 0. That's simply the y-axis. And then all of this is going to get revolved around the line y is equal to 4. So first, let's just find the region that's bounded. The region that's bounded by the red, blue, and green lines is this region right here. And this region is going to be rotated around the line y equals 4. There's the line y is equal to 4. So we're rotating about this region. So when I take that black triangle and spin it around that gray line, the reflection that I will make is another triangle that looks like this. So we're forming a 3D shape that kind of looks like a cone that has a circle cut out in the middle of it. Because it has a circle cut out in the middle of it, we are going to be using the washer method. That means that we have a capital R, a large radius that runs from the axis of revolution to the end, the bottom of the furthest limit of the region that we're rotating. That capital R, notice that if I were to extend it, it would be hitting the x-axis. We're rotating around a horizontal line. We have vertical representative rectangles everything in our integral needs to be in terms of x. So this is a capital R of x. We think top minus bottom. The top hits at 4. The bottom hits the line x. The blue line x. That's where the bottom is hitting. So we have our capital R of x. We will also need to find our little r of x. Little r of x is not in the region that we're rotating. It's the radius of the hole. We subtract the area that we would get from the radius of the hole. We're again going to do top minus bottom. The top is 4, the bottom is 3, little r is 1, right? So now let's go and find our limits of integration. We're going to be integrating everything with respect to x. I can see that this region starts at x is equal to 0 from the left, just this region in here. As a reminder, this region outlined in pink is the region that we're actually moving, right? That we're spinning around the line y is equal to 4. So thinking about the x limits for that region, to the left we start from x is equal to 0, so our lower limit of integration will be 0. Go ahead and set that up. The upper limit of integration depends on what this x value is right here. I can see that the y value at that point is 3. And remember that the blue line is y is equal to x. So that has to be the point 3, 3. So our upper limit of integration is 3. And then we will set up our capital R of x squared minus our little r of x squared. And we're integrating with respect to x. So we will be squaring 4 minus x and subtracting what 1 squared is. I will go ahead and do some algebra on the inside of this integral, just expanding this integrand. And then we will combine like terms on the inside of the integral. So 16 minus 1 gives us a constant of 15 minus 8x plus x squared dx. Now we'll go ahead and integrate each term. Increasing our exponent by 1 and dividing by our new exponent. And subtract, when we plug in our lower limit of 0, all of those terms will go to 0. And when we evaluate 15 times 3 minus 4 times 3 squared plus 3 cubed over 3, that simplifies to 18, leaving us with 18 pi as our answer.